Morning, y'all.
Good morning.
Morning.
Let's see. So I rolled out of the rack, 5 a.m. Grade tests. And unless your name is Connor, you'll be happy to know you're all done. So it's in my upper math. I was trying to discern where you went wrong on number 2, Connor, when the bell went off. So I'll have her done shortly. But I always felt like you guys put a lot of time and thought into this. It's like you don't want to wait a week. Let's get it done. Yeah. Well, got a black eye. I wonder if it still shows. Look like a black eye.
Into a bar fight?
One time this guy had a black eye and I was like, what happened to you? And he said, I fell in my eye. I was like, what?
That's awesome.
You can't fall in your eye. That's impossible. So now I can say, yep, fell in my eye. We were kayaking a hard run this weekend and I might have went over some rocks upside down with not my expensive, nice helmet my wife bought me, but my rather cheap helmet that I've had for 20 years. So it's my own fault.
You can't really tell over Zoom. You can't really see it.
I know with glasses on it's fine. I won't zoom in. I'm already ugly enough. So let's see, as usual, maybe you're looking at your test to see how you did so far, and which is fine. If you want to stay after class and look at it, I have them all kind of saved. I can pull them up and look it over. But as I've told you before, I spend forever looking carefully to find every little important or silly mistake you make, and I don't think I missed any. So as always, feel free to argue points if you like.
Hey Doug, mine actually isn't posted on Lab and Math.
I know you weren't listening. I was telling you at the start
God.
that I had everybody's done but Connor's.
I was getting coffee. Sorry about that.
No worries. I was on your number 2 when my time ran out. So yeah, you made a mistake on number 2, and I was trying to figure out why. It was something
No, I didn't. Really?
Yeah.
I checked them all in Desmos. They all checked out, I thought.
I know. I saw that. That's part of it. Is I go down those rabbit trails. Like I graph. Like I'll check that and see like how come he thought it was right and that kind of thing.
Oh no. Well, my goal is to beat David Schmidt on at least one test this term, and I thought this was it because we like looked it over at the end and we were like checking it all, and they all checked out in Desmos. I thought weird.
Yeah. Well, don't work so hard. Just send me $10 in the mail and whatever score you need.
Oh, gotcha. I see how RCC works now. Perfect.
Right.
Where I get all my points, Connor, I just bribed Doug.
I didn't know how the system worked. Gosh dang it.
David hasn't got one question right on any test, and yet he's getting an A. So
I haven't even taken the tests, dude.
well, dude, don't tell him everything. So you may have noticed if you looked at the syllabi, that suddenly we're going clear back to chapter 5. Why are we doing such things? Well, I will show you. Because Laplace transform is a tool that we could use in chapter 5. And so anyway, that was my philosophy. But good news is we're doing 5.1 today. And the even better news is 5.1 has no assignment. But what I really want to do is give you a really good introduction to what chapter 5 is about, which is actually solving systems of differential equations. Like we've been solving differential equations, but we're now going to solve systems of them. kind of right at the tail end. We're going to pick up a couple of, a few scraps kind of at the tail end. This is such a, you may have noticed I don't know, what did we get? A third of the book. And there's a lot of stuff we don't have time to cover. But so there's just kind of a few neat things I just want to throw in kind of at the tail end. Anyway, let's dive in. And that's also good. Let's see. I don't remember the top of my head. No, I can look. Project. No, I can't look. When's your project due? Today? Yesterday? I don't know.
I think it's on Wednesday.
That sounds right.
But
Yeah, it is Wednesday. So again, I want to invite you to, ask me questions. If I can shut up fast enough, maybe I'll even have time kind of in class before you technically have to leave. But I want all of you to get that right if possible. So anyway, awesome. So the intro to this 5.1 is not just a tank. Remember how earlier one of the inventions that caused the differential equation was looking at liquid flowing into a tank and out of a tank, and that created a differential equation that we're able to solve and then actually model kind of how the chemical changed in the tank. Well, this one's even crazier. And that is, what if you have an interconnected tank, or tanks, I guess you could say. So, and I actually just want to spend kind of forever just letting you think and reasoning, as I often do, to kind of introduce these things, rather than showing you kind of pat methods to solve them. And really 5.2 is going to be the cool way to solve these, but we can actually solve them entirely just based on what we know right now. So here we go. Interconnected tanks. Let's have a tank here. Let's step it up a notch. You guys did pretty good on this test. Let's make the tank actually isometric, a cylinder. Losers make boxes. We can do this better than that. So I have these two cylindrical tanks, and but this is nothing different than before. And we're going to call this tank A and this tank B. And we'll say this tank is 200 liters, whereas this tank is only 100. So they're not the same exact size, or at least the same amount of liquid in them. And let's see. Here we will let y of t be, and to keep this kind of simple, let's let y of t be the, what should we call it? Kilograms. Let's make it salt or something like that. Y of t is the kilograms of salt. So we're talking about saltiness in this water, kind of boring, kind of like examples that are making something cool in chemistry. But and over here we'll make x of t, because notice it's a totally different tank. So that's the problem here. We got an x of t and a y of t. So I'm going to just write y of t up here, write x of t up here. And then, of course, we have to have an initial condition. So let's say that y of 0 equals 10. Whereas over here, x of 0 equals 20. Those are, I guess I'll throw kilograms in there. So just to soak this in, so we have 200 liters of liquid in tank A and 10 kilograms at time 0 when we start, 10 kilograms of salt. The other tank, only 100 liters, but more salt. So does it make sense tank B is saltier? Because it's got double the salt and half the water, right? So it's way saltier, 4 times saltier, I guess you could say, if you divided them, right? If you made a concentration out of it, 10 divided by 200 and 20 divided by 100, that'd be 0.05 and 0.2. It's actually 4 times saltier. And so that's great. But remember, this is what calculus is for. right now, would you agree this is, well, static? When I teach calculus, I always say it's the mathematics of motion. So there, we do that. But the problem is now if we start having, pouring liquid into one of the tanks or whatever, then things start changing, in which case, for somebody who doesn't know calculus, you just have to sit there and stop and just wait till somebody turns the faucet off, and then you can kind of reanalyze it. But in calculus, you can say, no, I can still do this, even though things are moving. So I like to point out, you look outside, if you see things not moving, awesome. You don't need calculus. Anything out there moving, then you got to have calculus if you want to describe it. So let's get this thing moving. Let's get some junk pouring in. Let's interconnect these tanks. So let's send in 2 liters per minute of liquid. That is 0.7 kilograms per liter of salt. So we got water coming in at 2 liters a minute. We don't know anything about that water, but then we're told, oh, it's 0.7 kilograms per liter of salt. So remember, there's 2 rates here. There's the water rate, and then there's the salt rate. But we're only concerned about the salt. We don't care about the water. And let's also throw some liquid into this tank. Let's say this is 3 liters per minute. But this is pure water. So there's no salt in it. Now, of course, you should say, oh, that's cool, because the left tank, which was not very salty, is now going to get saltier, right? Because you're putting salt in it. Well, wait a minute. Is it going to get saltier? Well, it depends. Is the water coming into the tank more salty than what's already in there? In this case, it is. I'll let you think about that. So the left tank is actually getting saltier. But then the right-hand tank is actually getting less salty, right? Because you're putting pure water in it. So it's kind of diluting it. So they're kind of working toward each other. It kind of feels like maybe at some point they'd be kind of the same concentration or something like that. Now, the tanks aren't still interconnected, so let's interconnect them. Let's send a pipe between these two right here. And pump 6 liters per minute in this direction. And another one down here, except let's send it that direction with 4 liters per minute. And notice I can't say what the concentration is for those. So these arrows are really important. I can't say what the concentration is there because it depends on what's in the other tank. Does that make sense? And what's in that tank is changing. In other words, I look right here and say, oh, 6 gallons a minute is heading over here. Well, how much salt is in that tank? Well, 10 kilograms per 200 liters. But is it going to stay 10 kilograms per 200 liters? Like this was 0.7 kilograms per 1 liter. Is this going to stay 10 kilograms per 200 liters? No, because you're pouring more concentrated stuff in. So we actually don't know what the concentration is going that way or this way for the same reason. Now look at tank A. What's happening to the liquid in tank A? Is the tank getting fuller as the pumps turn on, or is it actually getting lower? What's happening to it?
Staying the same, isn't it?
Yep. Because you got 2 coming in on the left, you got 4 coming in on the right, and then you got 6 going out. So it actually isn't changing at all, which is nice. Remember how it was a little more painful when the level of the liquid in the tanks, that's going to stay 200 liters. That's kind of nice, right? What's happening in tank B?
Looks like the volume's increasing on that one.
Yeah, you got 3 coming in here, 6 coming in here. That's 9, and you only got 4 going out. So it's actually getting 5 more liters per minute going out. I'm sorry, coming in. But let's let's fix that and send out 5 liters per minute. Again, just to kind of keep it simple. And so now both tanks are staying the same liquid level, not the same salt. And we said earlier, it feels like tank B is going to begin to get diluted when we turn on the pumps. Notice there's 6 pumps here, 5 pumps. I mean, 1, 2, 3, 4, 5. Yeah, 5 pumps. And so B is going to get diluted and A is going to get more concentrated. But again, one of the interesting questions about this is like, what's the equilibrium? Like after time, is it actually going to reach kind of an equilibrium where it just stays kind of the same? It reaches a certain concentration or not? Woo. Okay, there's the setup. Your brain is in pain. Now, let's see if we can write some equations. Now, what this is going to produce is what I told you chapter 5 is about, which is actually a system of linear equations because we got 2 tanks and not just one. So let's see if we can figure this out. Remember the guiding principle behind all of this, if you will, is x prime equals rate in minus rate out. But then, of course, we also have y prime, right? My phone blowing up. Quiet. So that's no different. That's not terrible, actually. So I won't belabor this point a ton because you can write these equations, but you probably don't feel great about it, right? You probably kind of survive that, but you probably don't feel great about it. I guess I should say people are probably all over the place and feeling like, oh man, I never understood this very well. And it was already like a month and now I can't do it. Other people are like, no, I figured that out. It makes sense. But let's see if we can do this. So let me see. Let me pick the easier one first. So you take a stab at it. What would tank A be? What would its equation be? Well, it's rate of change y prime. And I can put t there or not. Certainly the amount in the tank is dependent on t. Its rate of change equals rate in minus rate out. But remember, it's rate in minus rate out of salt, not liquid. Take a stab at that. What do you got coming in? What do you got going out? So let me remind you that that one on the left is 2 liters. Let the units lead you to what to do. 2 liters per minute of water times 0.7 kilograms per liter of salt. So the liters cancel, and now you have kilograms per minute of salt. That's a rate of salt, not a rate of water anymore. So the rate of salt comes from the rate of water. If I had more water coming in, then I'd get more salt. because the water is salty, 0.7 kilograms per liter. So that's actually 1.4 kilograms per minute of salt. So again, just to stop and make sense of that, it's kind of like, oh, you mean after 1 minute, then this 10 is going to go up to 11.4? Yeah. Well, if it wasn't leaking out of the tank, I guess it would, right? If that was all that was happening, I'm getting 1.4 kilograms per minute of salt coming in. So 1 minute later, this is 11.4, and then it just goes from there. But unfortunately, it's connected to another tank. So some of it's leaking out. So I won't have 1.4 more kilograms because some's leaking out. But wait a minute, some's coming in. I mean, feel how complicated this is? Doesn't it feel like it'd be impossible to even make sense of this or make any progress? Well, that's not the only rate in. Isn't that 4 liters per minute also coming in? So plus 4 liters per minute. Again, that's just water though, right? Or just liquid. I don't know what's in it. But here's the tricky part. You know, what's this? Like that was our concentration, but what's your concentration in that other tank over there? Well, remember, X of T is the kilograms of salt, just like this was 0.7 kilograms of salt. So it's X kilograms of salt because see, that number is not a constant. It depends on what's in the tank per, not per liter, but per, well, 100 liters. Because remember, this tank is staying 100 liters. So that concentration is not a constant. So I'd have to say times X kilograms per 100 liters. Again, those liters will cancel and I'll get 4x over 100. Do you see that that is my kind of the in? There's sort of 2 ends. There's 2 pipes coming into this tank. One's a constant. The other is variable. And then the same thing happens for going out. Wouldn't going out be, here's my minus sign, rate out, minus what's going out? Well, 6 liters a minute. 6 liters a minute of liquid are going out, but what's its concentration? Well, isn't it Y kilograms of salt per 200? And notice again, it stays 200. So I don't have to say 200 plus T or 200 minus 3T or something complicated. I can just say 200 because it's staying 200 liters. Now, just to write that a little more cleanly, then I can just say Y prime equals 1.4. And again, I can just, in my mind, know that's kilograms per meter or per minute, or you could write that in there. Either one's fine. And the next one would be 4x over 100. Well, isn't that 0.4, 0.04x? Call it 1 over 25. I don't care what you do with that. Reduce it and write it as a fraction, write it as a decimal. Who cares? Again, kilograms per minute. And then minus 6y. The L's cancel. 6y over 200. That'd be 3 over 100. So that'd be minus 0.03y. So stop and think about the units just real quick. You know, what is Y? Y is the kilograms of salt. What's Y prime? Well, that's a rate of change. Well, then kilograms goes to kilograms per minute. So over here, I have kilograms per minute equals kilograms per minute plus kilograms per minute minus kilograms per minute. I mean, those are all the same units, which is why I can add them. I'm adding like terms, if you will. And so there's my first equation. But what's wrong with that equation? Like what's not good? If I say, okay, good, now solve it. Why can't you solve it?
It needs to be equal to something.
Be more specific. What do you mean? Like haven't we been solving things that look like this kind of all term? Why can't we just solve it? What does this have that nothing else we've ever done has had?
There's like 2 variables.
exactly. So if this y prime here kind of says, oh, working in y's, huh? So do I care that there's a y over here? No. But do I care that there's an x? Yeah. Like that x is what's killing me here, because there's two different tanks, and so there's two different, amounts, and I can't solve that. Like I can't solve an equation with two unknowns, and so that's why, again, this is called a system of differential equations. Notice it's a differential equation, but unfortunately, because these tanks are connected, there's two different unknowns in it. And you know this from algebra. It's like, well, I'm going to have two equations. And fortunately, the second tank is going to give us that second equation. I mean, the second tank is what caused the problem in the first place, right? That's why there's an X in here, because of the dumb second tank. So if I do this with the second tank, then I'm going to get another equation with X's and Y's in it. And then maybe I have, two equations, two unknowns, and somehow I can solve that. But notice again, it's a differential equation thanks to that Y prime right there. It's a derivative. It's the only access I have to this. Everything is changing. Okay, so with that in mind, let me give you some time again, and hopefully you can, if you didn't get the last one under your own power, I'm hoping that this next one you can. What's happening in the second tank, in the X tank, in the B tank, whatever? You got two ins and two outs.
Can you scroll it up slightly?
Is that what you're after?
Yeah.
So let's see, I'm catching up to you now. So wouldn't it be, let's see, you got 6 liters per minute of liquid coming in, and it is Y kilograms of salt per 200 liters, just like we had on the one above. That's coming in. What else is coming in? 3 liters per minute. But what happens here? This is interesting. Times what?
Is it times 0x over?
Yeah, that's exactly right. It's like there's water coming in, but like
Why?
there's no salt coming in. So there's actually nothing there. Like you could just leave this off if you wanted to. Again, we're trying, what I found the hard part of this is to not see the 3 liters per minute as a rate. Yeah, that's the rate of water, but we're not talking about the rate of water. We're talking about the more interesting question, which is the rate of salt. Because notice the rate of change of water is 0 because there's no water changing. The left tank stays 200, the right tank stays 100. There, if you want to talk about the rate of change of water, it's 0 and you're done. So we're talking about salt. And so, well, if it's pure water, then isn't it no salt? So don't even write it down if you don't want to, but I'm going to write it here just because don't you have 0 kilograms of salt in each liter as that comes in. So, that's your rate in.
So Doug, I was curious about that. Aren't we talking about the rate of change of salt though? So
Exactly.
like, wouldn't it matter? Like with the fact that we're just leaving out 3 liters per minute coming in, doesn't that affect I guess we're talking about overall salt then, huh? We're not talking about the solution and the mixture of it.
Yeah, I mean, if you want to talk about concentration, the fact that there's 3 liters coming in of water is definitely affecting the concentration, but it's not affecting the kilograms of salt. And that's why it's kind of important to note, that X is kilograms of salt. It's not kilograms per minute of salt. X is not a rate. It's literally a kilogram. It's a weight, an amount. Again, I found this hard too, so I'm kind of re-hitting those ideas a bunch. And then let's see what's going out. What'd you do with the 4 and the 5? Does it matter that one is 4 and one is 5? Minus 4 liters per minute of salt in that tank. What's in that tank? Again, it's X over 100. X kilograms of salt over 100 liters. And then isn't it exactly the same thing? Minus 5 liters per minute over times X kilograms of salt per liter. Notice they're both minus.
And you just combine that to 9 liters.
Yeah, aren't those like terms? So it actually doesn't matter as far as the tank is concerned. It doesn't matter that 4 is going out one pipe and 5 is going out the other. It's just 9. Now, if I switch those, I'm not going to do this, but if I switch this to 3 and this to 6, this tank wouldn't notice, but this tank would no longer stay at 200 liters. Does that make sense? So that would affect things, but it just doesn't affect the amount of salt. So basically that's just 9. Okay, so what does our X prime equation look like then? X prime equals, the L's cancel, 6 over 200 is 0.03. So you have 0.03 Y from this term, and then actually nothing from that term. And then minus, let's see, I guess that would just be minus 9X over 100, or minus 0.09X, I guess. Are you able to agree that that is now our system of equations? Now, of course, the book assignment in 5.2 just says, hey, wouldn't it be fun to solve a system of differential equations? They just give you like 2 equations like that and say, go solve them. The point of 5.1, and this book is organized, in my opinion, kind of cool. Like it has a whole chapter at the start of every section devoted without questions in the back of the book just to, who cares? Like, why would you ever do this? So 5.2, we're just going to practice like getting good at solving these, but this section is more about like, why would these ever come up in the world? And so it's kind of cool to think about. So now we sort of switch gears and say, okay, I've got these 2 differential equations. I don't really care where they came from. Now I just want to try to figure out, is there some, and of course, do you understand what I'm after here, or what you're after here? I would really like to find an equation for y of t, right? That's what I'd really like to find. And x of t, because that's going to tell me how much salt is in each tank at any time I want to know, right? And of course, on the other side, I want t's, right? I want y of t equals whatever, e to the 4t plus 6t squared minus 7, whatever. I want what we've been wanting the whole term, some equation. And that's what's implied when you say y of t and not just y. I want t's on the other side. No x's. I don't want any x's over there. I just want y of t. So I can plug in a time and then bam, I know how much salt is in that tank. Because remember, in this case, we are actually pumping between these 2 tanks. And I've been in one of the factories in this valley, and they have a lot more than just 2 tanks pumping into each other and so forth. And I just found it super overwhelming. Pipes everywhere in the rafters. And it's like, my God, who can understand this stuff? But the goal in this would probably be to turn the pumps off, when you changed, because you're obviously just looking at that saying, oh, I don't want the the concentration. The concentration in tank A, as we said, is 10/200, which I guess is 5/100, which is 0.05 kilograms per liter. That's the concentration in that tank. And maybe I don't want that. Maybe I want some other concentration. So, I turn it on. Or maybe this is something natural, like, a lake, something of that nature, where you're not turning it on. It's just kind of happening. One lake flows into another lake, that kind of a thing. Or rain comes down while the river flows in, that kind of a thing. Maybe it's natural and you sort of don't have control over it. But the main thing I want you to just think about is this is pretty contrived in the sense that we're pumping it in such a fashion that the lake is not filling up with water. It's just staying exactly the same amount comes out. And it's also implied in this too, unlike a lake, that these are stirred up, remember, because if the salt comes in and just sinks to the bottom, then it's much tougher to kind of figure out what's going on, right? We're assuming it comes in and dissolves and immediately changes the concentration in the tank instead of sinking to the bottom and taking 10 minutes before it actually dissolves. And I mean, as challenging as this question is, it's actually a gross oversimplification of what's really happening. So algebra. Is there some way? Now, what you would have been happy with, I don't know if happy is the right word, but what you would have been happy with in this equation is, since there's an x prime here, you'd have been happy if this was an x, but then again, we're not happy that that's a y. And so if I could somehow put these together so it was only x's or only y's, then I'd be able to solve that system, right? But right now, I'm going to have to put them together in some way to do that. I just want to give you a second to kind of think about that. This isn't terrible. This is just basic algebra. You can totally do this. But it doesn't mean what you guess and try the first try is actually going to work. So I just want to let you think about that for a second rather than just immediately showing you. Anybody try this? I noticed that the first equation has a negative 0.03y, and the second equation has a positive 0.03y. So why not just try adding, the mathematicians would call that elimination method. We did that before. Again, that's just kind of the, hey, you have 3x plus 2y equals 7. I'm going to erase this. And you have 6x minus 9y equals 8. And so you say, oh, those would be the same x as if I multiplied by -2. So I'd have negative 6x and plus 6x, and I could add them in the x's. There'd be no x anymore. In our case, though, they're already negative. Like they're one's positive, one's negative. They're the exact same size. I don't even need to multiply one of them by anything. So that seems like a pretty good idea. On the left side, I get y prime plus x prime. On the right side, I get 0.04x minus 0.09x would be minus 0.05x, and then sweet, add the y's, they're gone. But that didn't work because I still have x's and y's. And it's even worse, actually, because now I have two separate derivatives. It's kind of worse than it's true. You need to understand algebraically that this is true, but not helpful. Do you agree with that? Really looking for an equation with only x's or only y's. Anybody have any good ideas? Or
No, it's a good
ideas at
idea.
all, even
Yeah.
if they aren't good?
Mine's probably that, but I'm wondering what would happen if you just subtracted the x prime to the other side, because that would kind of give us like a pseudo, differential equation looking just y equals x prime minus 0.05x and then plus 1.4, and then we take a look at the Laplace transform of it. Because you can take the Laplace transform of y prime is my thought,
Yeah. You're still going to have the problem that you've got x's and y's though in doing that. But you're right. If you subtract x prime, at least the left side is y prime and the right side is x. That seems to be worth something. But the problem is you still have x's and y's. And if you still have x's and y's, no matter what form they're in, even if there were no derivatives, and the derivatives make it even worse. But if there were no derivatives at all and you had x's and y's, you wouldn't be able to solve this. One equation with two unknowns is not going to be able to be solved.
It wouldn't be true to set x prime equal to 0, would it? Because it's just changing, I guess.
That is not true, only because you're basically saying then if you say x prime is equal to 0, then you're saying, hey, there's no change in that tank.
Yeah.
But
Yeah,
it is
okay.
changing, and so it's kind of a lie.
So it'd be ugly, but if we did the same thing that I just said to subtract the x prime on the other side, couldn't we substitute what's on the right side for y prime? Because that equals y prime, right?
Yeah, remember you got two equations to work with. In other words, if you solve that new equation, remember we just made a third equation. It's a different equation, but it has the same answers that the previous two do. So it's almost like we have three equations to work with now, not just two. And so that's still true. And so if I solve that for y prime, sure, now I have y prime, and it's made of a bunch of x's. If I can use that, absolutely.
Would it be helpful if we integrated both sides with respect to the left side, I guess? So that way we just get y equals ugly stuff and then x equals ugly stuff.
Yes. Let's see. Let me think about that for a second. Keep in mind that y and x are functions, and I don't know what they are yet. Like they could, and you kind of know what they are because they're like e to the 3t's and maybe sines and cosines. I mean, stuff like that. It's functions, but they're functions we don't know what they are. And so if we say, hey, let's integrate y prime, then I can say I'm going to integrate it, but I can't actually do it because I don't know what it is yet. Does that make sense?
Yeah, I'm just spouting whatever comes to my head.
I love it. That's exactly why I'm trying to give you time to think rather than just immediately showing you what to do. And this is not terrible. Like, this is just algebra. You don't have to come up with something brilliant here, but it's kind of brilliant. But when somebody proposes it, even if that's me, you're going to go, oh yeah, I should have thought of that.
So what I did is solve for y in the bottom equation, and then took the derivative of all that. So you were able to get an equation with y and then an equation with y prime as well.
So you're saying kind of like what Connor said, you know, I can solve
Yeah,
equations
same
for
kind of
whatever I
idea.
want to. And so could I substitute? This is kind of what I think Ben is saying. And notice I don't know if this is going to work. I mean, I actually do know, but I'm just trying his idea. So he's saying I took the second equation, solved it for y. So let's see, that'd be 0.03y equals, and I'd add that 0.09x to the other side. And I can divide by 0.03. So let's see, dividing 3 is 300, so that'd be 100/3. So you are able to solve that second one for y. And while we're at it, couldn't you also solve the top one for x? Notice you can't solve the bottom one for x because there's an x and an x prime, but there's only a y. So you can solve the bottom one for y. The top one you could solve for x, but you couldn't solve for y because there's a y and a y prime, but there's just one x, so I could solve the top one for x. Now, what good does that do me? What was your idea, Ben? Like, how am I gonna put that in places?
So now we have something to plug in for y. But if we take the derivative of both sides of that, then we have y prime, and we have something we can plug in for that.
That seems to be worth pursuing. In other words, he's saying if I took it back to this top equation up here, now that I know what y is, couldn't I plug it in right here? And now there's no more y's. Now there's only x's. That's progress. But then, oh no, there's a y prime over here. Well, couldn't I take the derivative of this? And then I would be able to plug it in made of x's too. That seems like it's worth trying to me. So since that's true, can we find y prime? Now keep in mind, what does y prime mean? It's dy dt. In other words, you're taking the derivative with respect to t. It's not dy dx. So because I don't think that's obvious, I'm going to write that out. We're taking all of our changes with respect to time. And so I'm going to do the same thing on the other side. What's the derivative of x prime? Isn't it another prime? And again, that's x prime prime of t. And then the derivative of 3x is the derivative is 3x prime. So don't I have y made of a bunch of x's? And now I have y prime made of a bunch of x's. I actually think this might work. So sub these into kind of the equation 1 up there. I guess I have to write 1 now since I said that. Okay, so let's see what that looked like. That would be 100 over 3 x double prime plus 3x prime. There's the y prime on the left side. Then it's 1.4 equals 1.4 plus 0.04x minus 0.03 times whatever y is, which is 100 over 3x prime plus 3x. At a glance, does that look better to you? Does that look like we can solve it? It should. You should say all x's, but then interestingly, it's actually turned into a second order differential equation. Isn't that kind of cool and surprising? But it's like we know how to solve second order differential equations. And by the way, that's why I stuck this after chapter 7, because you have 2 methods for this now. If you're a Laplace guy, gal, then you can say, I know how to solve these. I'll use the Laplace transform both sides. No, I don't like that. I like the kind of guessing technique. At this point, you got a note sheet if you kind of like the cheat approach, or you can take the Laplace transform. So let's see. What do we have if we clean this mess up? Now, I don't like fractions, so this is something I find myself wanting to think about right away. I don't like decimals. I don't like fractions. So there's some way I could kind of clean up that disaster. So I'm thinking about that right off the bat, but I still have to distribute this 0.03 in. So I'm going to kind of wait to do that, but just to kind of clean things up a little bit. Let's see, I got 100 thirds x double prime plus 3x prime is 1.4 plus 0.04x minus 0.03 times 100 over 3. Let's see, that's 300ths. 300ths times 100 thirds. Does that just cancel and become minus x prime? I find myself not trusting that, even though I think I'm doing it right. Times 100 divided by 3. Yeah. And then 0.03 times 3 is 0.09, so that'd be minus 0.09x. And I don't like the fact that there's a 3 in the fraction on the left-hand side, so I'm going to multiply everything by 3. And if I had a brain, I would actually, some of you should pay attention to this because you do the same thing. Before I go doing that, maybe I should collect like terms together a little bit. Like, don't these two belong together since they're both like terms? So maybe I should at least think about that. And maybe I could even add this to the other side to have a total of 4 of those. So this would be 100x double prime. There'd be a 4x prime on this side, but times 3, that'd be 12. And then I have 1.4, but I got to multiply that by 3, which I think is 4.2. This is why I make a lot of mistakes. I do too many things in my head. And then there's actually a negative 0.05x, but I'm multiplying that by 3. So would that be negative 1.5? 0.05. Negative 0.15. And then that's still 1500. So I'm trying to decide, should I multiply both sides by 100 now? I don't think I will. So I'm just going to write here, multiply by 3. That's what I'm doing here. Now I'm going to multiply by 100. Again, I don't know if this is a good idea. You should disagree with that. You should think I wouldn't do it that way. Good. You're far enough in math, you should have your own opinions about algebra. Oops, that's an equal sign. Equals 4,200 minus 15x. And again, I'm kind of questioning myself now too, kind of like, man, those are pretty big numbers. Maybe that's a bad idea. I should just left them alone. Like that's pretty. understandable, but I went this far. It looks like they're all divisible by 5, doesn't it? So I'm just doing algebra because I got to plug all this in the quadratic formula for the, auxiliary equation. I mean, I'm just thinking about stuff like that. So if I divide 10,000 by 5, of course, that's 2,000. So I have 2,000 x double prime plus 120 divided by 5. Isn't that 4? I don't trust myself. It's 240, yeah. 240 x prime. 4,200 divided by 5 is 840 minus 15 divided by 5. And I think that's it. I think that's as far as I can go if I want whole numbers. And what you should think is now, I know what form to write this in. I want to write it in this form, 2,000 x double prime plus 240x prime plus 3x equals 840. Hey, look, a non-homogeneous second order differential equation. And so I'm going to be able to solve this and find x of t. Now you may remember, what was our goal here? We also have to find a y of t. Like, this is a lot of work, but we're only going to be half done after we solve this. We still need to find a y of t. We want to know what's happening in both tanks. And so that's on the back burner. So again, kind of what's your opinion of this in terms of, like, let's get this done? Because our focus here is on a tank. Like, I'm just interested in the tank. Are you a Laplace transform person, or are you thinking kind of the cheat method makes more sense? Because it's not as fresh in our mind, I'm going to go back, and also because I think it's faster. If you allow yourself to use the note sheet, if you will, and kind of cheat, then it's actually faster. So remember, there was 2 answers to this. The homogeneous answer. And if I quickly take the auxiliary equation, 2,000r squared plus 240r plus 3 equals 0. And I just put that in the quadratic formula because it's in my calculator. 2,000, 240 plus 3. I got real answers. That's awesome. I'm really happy about that. And I hope you understand why I say that. I'm really happy I got real answers. I got negative 0.0142. And I said approximately because I chose to round that off to 4 decimal places. And I did that because it's a really small number. Next one was 0.1058. I could call it 0.1, but it just feels like, man, that number is so small that 58 might make a difference. I could call it 0.106. Again, I don't care on a test. Just depends on, like, how much do you care about the accuracy of what's in the tank. If it's just salt, yeah, you might not really care that much. If it was something really important, maybe 4 decimal places is not enough. But why am I really happy that those are real answers? Well, because I don't have to work that hard. Like, I don't have to do the sines and cosines thing. Remember, if the answers are distinct real answers, then I'm done. Kind of my x1 equation with respect to t is c1 e to the negative 0.01442t plus c2 e to the negative 0.1058t. So there's my homogeneous answer. And then there's my kind of my educated guess, my non-homogeneous answer. Do you know what your guess is for this? What would x1 have to be? It's not really a guess. We know guessing was when we weren't sure. We know for sure now. What's our x2 equation equal to, given that what's over there doesn't have e's, doesn't have signs, doesn't even have a t?
Just any constant.
Exactly right. It's just some constant. So if that's your guess, then in order to plug it back in, remember we've got to have an x prime and an x double prime. And so if I take the derivative of that or the second derivative of that, of course, I'm going to get nothing. That's really good. So if I plug that back in, then I just get, hence, I just get 3 times a, since my guess is a, equals 840. And because your teacher likes you, when you divide that by 3, you get a whole number, 280. So that means your x2 of t equation is equal to 280. And notice it's x2 of t, but yet notice the time doesn't matter. Doesn't matter what time it is. It's always 280. I'm doing something wrong. For some reason I have in my head that's 84. Is there anything wrong with this? Yeah, there is something wrong with this. Back here, when I multiplied by 42 by 100, that is 420, not 4,200, which makes that 84. I'll just fix all that really quick since it's not terrible to do. And when I divide 3 by 84, I get 28. There, fixed. I got kind of lucky to catch that, right? Remember, that would have cost me a whole bunch of time. So that means my x equation as a function of time is equal to, well, just these two things added together, right? So there's the equation. Now, is there some way to find C1 and C2? Do I know anything? Do I know anything about this? Do I know any initial conditions? Yeah, you do. However, for second order differential equations, you just took this last test, didn't there have to be a y, like an x of 0 and an x prime of 0? Like that's one, I got two unknowns, a C1 and a C2. X of 0 being 20 is not going to be enough. And so that's cool, but I'm a little troubled. So I kind of have, again, what might be called the general form. I'm going to go back in here and write a little g in there because I have the general form. No matter what the initial conditions were in the tank, this is the model for that tank, no matter what the initial conditions were. But I do know that x of 0 equals 20. So I guess I could say, hence, since t is 0, e to the 0 is 1. So doesn't that tell me C1 plus C2 plus, well, 28. There's a 28 there too. That equals 20. So C1 plus C2 is -8. But I can't solve that. That's two unknowns. There's all kinds of answers to that, right? -4, -4, -8, 0, -3, -5, 10, -18. Can't solve that. Anybody have any brilliant ideas. If I go back here as a hint, look at those two equations. Is there a way to find x prime of 0? In other words, what's the initial rate of change? That was not given. That was not something I would know. There's nothing in that original design that would just be like, you just know it. You don't just know it. But doesn't this right here, isn't that what we need? X prime of 0? Is there some way I could know that?
If, yeah, we plug in everything is 0, then we can plug in y of 0 and x of 0 into there.
Yeah, that's exactly right. So that's rather surprising. Ooh, you got a long way to go. Get on down there. So here's one of my equations. But remember, these are t's. In other words, this is really y of t. That's x of t. This is x prime of t, right? So what's x prime of 0? Well, that's 0.03 times, well, y of 0. But don't we know y of 0? And isn't this 0.09 times x of 0? But we just looked it up. Isn't x of 0 equal to 20? I forgot what y of 0 was. Ooh, 10. So that means x prime of 0 equals, what is that, 0.3. Let's not screw this up again. Minus 1.8 or minus 1.5. That's pretty cool. It's really cool. But of course, what's not cool is, remember, in order to use this, I have to have an equation for the derivative, which means, yeah, you're going to go take the derivative. If you're a true mathematician, you're excited about that. I got to take the derivative. Well, fortunately, that isn't a product rule or anything terrible, but at least it's a chain rule. The derivative of e to the junk is e to the junk times the derivative of the junk. So doesn't that 0.0142 come down front with the C1 to be multiplied by? So there's the derivative of the E junk, and then the same thing happens again with the other one. You end up with minus 0.1058 C2 times e to the negative 0.1058. Looks like a 6. That will not do. And so I can say that x prime of 0, which we now know is negative 1.5, equals negative 0.0142 C1, since e to the 0 is just 1, so the e terms again drop out, minus 0.1058 C2, also times 1. So there's my second equation. So now I've got 2 equations, 2 unknowns. Because this is, such a complicated problem and I do not want to get it wrong, I'm going to throw all of this into the matrix. So 1C1 plus 1C2 equals negative 8. And then negative 0.0142 C1 minus, notice they're all actually minus signs. I could change them all to plus signs. I think I will. I hate minus signs. And 0.1058, that equals 1.5. So I can throw all of that into the matrix. That doesn't take super long to do. Also gives you time to think, kind of take this all in. 0.11 negative 8, 0.0142, 0.1058, 1.5, second quit, second matrix, math, reduced to echelon form, second matrix, A, bam. This gave me that C1 is approximately, and I say approximately because the 0.0142 was approximate, so I can't be definite about this. There's no reason to ask it for a fractional answer. So again, I don't know how to round this, but I'll call it negative 25.616. C2 is approximately negative, positive, sorry, 17.616 as well. That's interesting. I wonder if that's a coincidence that they have the same decimal after them. And so now I actually own the tank. Like I'm done. I figured this out. As I said, we're half done because we found X, but if I back up here, it's like we had the general equation back here at one point. Well, now we've got the X particular equation. We own what's happening in that tank. That is really cool, I think. Negative 25.616 e to the negative 0.0142t plus 17.616 e to the positive point, no negative again, 0.1058t. So mission accomplished. Wow, that's an amazing amount of work. Like, in the real world, notice we're an hour and 15 minutes into this and we haven't even finished the problem, right? We're only sort of, in one sense, halfway done, maybe a third, because it took a bunch of time to set this up in the first place. But it's like, you'd have to really want to do this in the real world. But it's amazing that we actually just found a model for this. Show you something kind of interesting quickly, because I already stuck this in here. I rounded those a little further, but looks like everything else, got it all right. That's amazing. Notice there's some things we like about this graph. One of them is, notice at time 0, it's indeed 20. But could you tell me, like, why? Notice it went down and then it started going back up again. Is there some reason why that would be the case? Why would it go down? It's like losing salt. It started with 20 and then it went down, down, down. Notice it looks like it kind of bottomed out. Let's see, what would that be, around 12 or something? It's like it bottomed out at 12 kilograms of salt around 20 minutes in, somewhere in there. And then it started actually going back up again. Why, does that make any sense why it would do that? Like, based on what was happening in the original problem? Well, remember we did say that it was more concentrated than the other tank. And then what did we do? We poured pure water into it, right? And then what was happening? What about this water that was coming in from the other tank right here? Well, isn't it more diluted? This is diluted compared to the X tank. And this is, pure. So yeah, of course that's going to go down from both directions, the pure water coming in and then the less concentrated salt coming in. So then why would it go back up? That seems weird. It just seems like it would go down. But keep in mind, this tank over here is increasing in concentration, right? It started out 10 kilograms per 200, but isn't really salty water coming into it, which means by default, isn't that saltier water coming over here? Again, stare at our equation right here. This is kind of cool just to point out, but answer this question. Oh, didn't I leave something out? I did. Remember that 28 back there? Forgot that. Let's check that dude in at the end here. I should have wrote smaller. Plus 28. What is the limit of x of t as t goes to infinity? In other words, if you just turn these on and left, as t goes to infinity, what happens? Easier for those of you that had Math 253. But we've done a bunch of this lately. The last two questions on the test asked you to plug in e is infinity. Since those e's are raised to negative exponents, then they move to the bottom of the number. So you have 25 over e to the 0.01t. You have 25 over e to the infinity. You have 25 over infinity. That's going to 0. The 17.6 is going to 0. So therefore, it's on its way to 28. That's what should happen. Well, notice that in this graph, that's exactly what does happen. Notice that you can't see exactly 28 here, but notice you can tell it levels off. And I could go in here just for the fun of it and say y equals 28. And then you'd actually be able to watch it happening. Notice it's on its way back up as the left tank gets more concentrated and starts pouring concentrated water into the tank. The fact that the pure water is going in doesn't matter anymore, but now it's actually getting more concentrated. And so it actually ends up going up. And so, yeah, that kind of fits. It starts at 20, starts at 0.20 like it's supposed to. And it actually ends up at 28 like the equation would have proposed that it ended up. That's kind of cool. Interesting. But of course, we're only half done. So how am I going to get the other one? I just have to start all over and like do this all over again. Let's go back to here. Except remember, I mean, just think about this for a second. I'll erase this, but if you were sitting here with like, 2x plus 3y equals 9 and 4x minus 5y equals 7, and you put them together and you found out y was 2 or something like that, what do you do once you find out y is 2? In order to get x, do you start all over and like eliminate? Do you start all over at the beginning and re-eliminate like a totally different letter? No, you just take that and plug it back in. To which one though? Which one of these do you plug this back into? The first one or the second one? And of course, the answer to that is it doesn't matter. If you really want to make sure you didn't screw up, plug it into both. So don't I have the answer now for x? Don't I have this answer right here? Don't I know that now? It's like a big equation, right? With a bunch of e's and junk in it. Why is it a bad idea to plug it into the first equation though? And a good idea to plug it into the second one? In terms of like, I want to be done. Let me go home. Well, if you plug it into that first one up there, notice you still have a y and a y prime. But if you plug it in here and its derivative in here, which by the way, we had to take a minute ago, then you have an equation with y and you're done. There's only one y in that. So it's going to be much easier to plug it into that second equation. Do you see that? Doesn't matter. But I'll still have to take an integral, if you will, to solve the first equation. What was your thought, Ben?
I said it wouldn't be like the most easy just to go down to where we actually solved it for y already and just plug in x prime and x into that.
That seems like a really good point. Like, didn't we, yeah, like right here, like maybe right here, even one of the creatures that we made, like maybe that'd be an even better place to plug it in, right? Because it's already solved for y. So that's an even better idea. I like that idea. Let's go with that one. Come on. So to find y of t, plug x of t back in. We'll even say to the easiest equation you find. And I think Ben's right. It's that one. Now, this is still, ugly. It's like there's a lot of algebra to do there, right? And although I did find the derivative earlier at the time, I didn't know what C1 was, and now I do. So it's almost like I have to take the derivative again. So I have my x. So my other ingredient is going to be x prime. So let's go find that. What's x prime of t? So of course, I'm going to take 25.616 and multiply that by 0.0142, which is 0.364 approximately, positive 0.364 e to the negative 0.0142t. Everybody understands that, right? The derivative of e to the junk is e to the junk. Then I had to multiply 0.0142 times 25. And then the same thing on the other one. I'll take 17.616 and multiply that by 0.1058, which is 1.864, but then it's going to be negative. And then, of course, the derivative of 28 is nothing. It's gone. Maybe I'll write a plus 0 here just to highlight us to that. So if I plug, of course, this, let's switch to a different color here. Of course, if I take this business and put it there, and I take all of this business and put it there, then I'm done. And maybe I'll have to collect some like terms together or something. So since it's all decimals anyway, why not just let the calculator, and of course this would be the particular solution of t, and I'm already done. And isn't that kind of interesting? I don't even have to plug y of 0 into this. Isn't that kind of weird? Because I have it solved for y, not y prime. So I'm going to risk it. So I know it's 100 thirds times x prime. So 100 thirds times x prime, 100 thirds times 0.364. That's my e to the 0.0142 t term. But then to that, I have to add 3 times the x term. So, boy, this feels dangerous. So 3 times this term, and I'm going to add them together. So that'll be 3 times that, like negative 75 that I'll be adding to that. So it'll actually be minus 3 times 25.616. So negative 64.715. That's my e to the negative 0.10142 t term. And then again, 100 thirds times x prime. So 100 thirds times negative 1.864. But then that would also be added to 3 times 17.616. Negative 9.285. And then notice 3 times 28 as well. Don't forget that. So that's 60 and 24. That's 84 plus 84. So notice right now, I know that the equilibrium for that one is going to be 84. When time goes to infinity, that's going to end up with 84 kilograms of salt in it. So the first tank has 84 kilograms of salt and the second one has 28. That's the future if they're left to run forever. I don't trust myself, so let's go see negative 64, negative 9.28. If I got that right, it'll be surprising. Oh, good, I did get it right. So let's take a look at that second tank. That's just kind of cool. First of all, notice, hey, good, y of 0 is 10. It was supposed to be 10. Why are you not surprised with this graph? You should think, well, it started out really low concentration, but then it had super high concentration salt going in. So it's just going to get more and more and more and more salty until, notice, hey, look, it's leveling out at 84. I won't take the time to graph that, but you can kind of see it's leveling out there as the equation would have predicted. So if I turn them both on, isn't that kind of fun just to kind of see the two tanks? So there actually is a place where they had the same amount of salt in them. Notice you could figure out what that was. And there's a bunch of interesting questions you can ask here, like what's the lowest that green one ever got, because it went low and then it went back up. And you could ask when, what if your goal was to like have them be the same so that you could, use that for something. So it's like, oh yeah, turn that off. Notice I can tell it's between 2 and 4 minutes, and I'd have to do some more algebra to get that exactly right. Or if Desmos was involved, hey look, I just cheated. 3.4 minutes, 15.87 kilograms of salt were in both tanks, at least for a second. And then the purple one began out racing it and the green one kind of dropped off the truck. But it's like there's all kinds of interesting philosophical questions you could ask or answer, kind of extra credity sorts of questions about this. But overall, your brain should just be hurting, right? That's what's really happening here. I think I'll snap a shot of that and throw it in the notes. It's so easy to do.
It would be interesting to like solve the original equation using Connor's way, because it seems like that would work, but then it seems like you'd just get a first derivative and not a second.
So you're saying you're saying that method that I maybe
like instead
busted
of
away too quickly, so to speak.
I think his was like instead of taking the derivative, you just substitute in substitute in for y prime and then substitute in for the other one.
Speaking as someone who follows my ideas for my entire life, it'll probably end up harder.
You have to live with you all the time, do you, Connor?
Yeah, I have to go down these rabbit trails all the time, and it never works out.
Well, those are important to go down, and the fact that this took an hour and a half, and of course, I went slow and explained it and tried to give you time to think and so forth, but it's kind of hard to imagine it getting worse. But you're not wrong, it could. Now, that is a pain. Like that method is a pain. And then what's cool is I'm going to show you something tomorrow. 5.2, there is a technique that mathematicians have come up with to solve this that actually isn't quite so ugly. We actually just, I don't know, in the end, what we just did here is we did this in what I would call blue collar style. Like we just took skills we already had and we ground it out, and maybe that's the only way there is. But the idea that if this is either important for a practical problem or interesting just because you're a mathematician, is there some easier way to do this? I mean, that this is begging for an answer to that question, right? If there was, it would sure be nice to know. And again, because classes like this are tours on well-trodden ground that other mathematicians have ran down for hundreds of years, books are all organized sequentially, and it's all scripted, and 2 minutes and 10 seconds into the tour, you should be in this location. we're going to turn the page and immediately begin looking at the answer to that, which probably took 100 years for somebody to come up with. And, brilliant people, all kinds of interesting histories. People had families and lived and died and were happy and sad. All this stuff was getting created. It's just weird to kind of flip the page of the book and immediately begin doing it. But I say that because if we back all the way up, as I said, tomorrow, what's going to happen is just going to be given a problem like that. There's no application or anything. It's just, hey, go do this. So there's going to be, y primes and x's and x primes and y primes and all of that to go kind of tackle. So I say that just to say, why don't you, if you're an interested person, you're a mathematician, don't just immediately read the next section. Although if you're like me, you might find that hard to do anyway. See if you can improve on this, because it turns out that would be a hopeful thing to do. There actually is an easier way to do this that won't take near as much time, near as much paper. But very profound, I think. Other things that, and I guess I'll just kind of say this for the fun of it. We're getting toward the end of this class, but I just mentioned a few of these, but things, other rabbit trails you might run down. So I'm just thinking out loud here. So one is like find a shortcut. And I'm telling you, there is one. Calculate the minimum of the xt graph. When I say calculate, I would hope you would think, hey, calculus, I know how to find those. I take the derivative, set it equal to 0. That's how I find maximums and minimums. And so go do that. Bring that back. Bring your calculus skills back, algebra skills. Like, those are just good things to do. Or as I mentioned before, algebraically find the intersection. And when I say extra credits, like, go do these and send them to me. Go hunt for, and I would think this would be kind of hard to do, but it's a curiosity I have. Go hunt for genuine applications of this. Because doesn't this feel a little contrived? Like, why would you do this? Like, why would you have 2 tanks and pump liquids in and out of both tanks? Is there any way to, and actually, I don't know the answer to this question. Like, it could be that tank I just drew you is like a total mathematician's contrived problem and nobody ever does this in industry. Maybe there's natural examples, like I said, of, like this room in the house, and then there's another room, in a business, you have like this floor and another floor, and chemicals are kind of, air with some kind of chemicals are flowing back and forth between the 2 floors. Call it COVID, since we're all getting COVID. Is there some natural scenario where this kind of thing happens? At least, roughly. It doesn't have to be exact, but just, yes, as I've told you, that's kind of what gets me pumped about math, is seeing where I could actually build something that other people couldn't build as a result of knowing what I know.
First thing that comes to mind is like heaters, right? Don't they do that where they take hot air from one room to make cold air in another?
What was I heard heaters?
No, heaters are like AC
Heaters.
units.
Right.
Like, I think they do. I know it involves 2 rooms and you have to like balance the temperature, and like one is drastically different than the other, like colder or hotter, and it pumps it into the outside air.
So an example might be like I'm in an office right now, and because that's a reasonably large room, there's a vent in the floor. So, this room gets air because it's got it's assumed that somebody's going to be living in it. So we got to keep that room cool. But there's some rooms in a house that are really tiny, and so they don't get one, like your closet. Maybe in a bedroom you have a vent in there, but there's none in the closet. And so, maybe the door of the closet is shut. So you have conditioned air. So it's temperature we're talking about now, 70-degree air blowing into the room. And so that's what's going into that room. But then air is going kind of under the door, passively, I guess you could say, passively going under the door into a room that has a different temperature of air. And so they're, interconnected in that way. I mean, that's exactly what I'm talking about. But again, the weird thing is, it's like, how do you, when I say passive, does it make sense if that closet is closed and there's no open windows in it? There's no incentive for air to go under the door because it's already full of air. Air seeks to equalize pressure. And so it sort of feels like, man, that'd be hard to conceptualize. But yeah, it's exactly what I'm talking about. Like I said before, lakes, is there like a tank next to a lake? So the lake is kind of a tank, but then there's also a tank next to the lake that is, doing some job or whatever, holding water for something. I don't know. It's just interesting. The other thing that it kind of occurs to me is, like, do that with the plus, like go back and kind of consider it all with the plus, or remember, like in my case, because I already did this earlier and kind of because it takes so much time to type, I went into Desmos and already typed it in, so it didn't take so much time. In a sense, I kind of got lucky and didn't make a math mistake. But if I was by myself, or this was actually modeling something, really valuable, really expensive, I could go back and check this now. It'd be kind of interesting to plug both of my answers back into those two equations and actually see if it was actually true. Because it almost feels like, wow, how could that possibly be true? So realistically, I took the answer think about this, see if this makes sense to you. I took the answer for x of t and I plugged it back into this equation right here. So if that first answer was wrong and I plugged it into this, producing another answer that's wrong, does it make sense? I wouldn't know that. It's not like that wouldn't have produced the answer. So the question would be, what if I went back to this one now? I sort of already know it works in the second equation because I used the second one. I used the second one to make the second answer. But if I went back to the first one and actually both of them worked, then that would be kind of proof that I didn't screw it up. And of course, if you were modeling something for money, a building you were designing or something, that would be worth the time to do, I would think. So if I say check solutions in equation 2. No, that was equation 1, wasn't it? It's just interesting. And I don't mention these actually because I want you to do extra credit. If I'm you, I'm thinking, oh, it's only another week of this class. I got to get out of here. My brain is full. But more just like, this is why you do math, or these are just the real mathematics is asking your own questions and then trying to answer them yourself. Stopping like I do all the time and say, does this make sense? Does it make sense that one went down and then went back up, whereas the other one just went up? Yeah, it actually does make sense. So there's a part of me that kind of feels like, man, I think I did that right. It kind of makes sense. It's working. Speaking of things making sense, so I don't know if I can answer this. I'm just going to think out loud for a second. Let's see, 2 liters per minute times 7 kilograms per, there's 1.4 kilograms per minute coming in. So I'm wondering if I can figure out what's in that other tank. That feels too complicated. What I was wondering is, could I get the 28 and the 84 somehow? I mean, they came up in the answers, but I'm just saying, if I went clear back to the start, is it like, yeah, that would be 84? You see what I'm saying? Notice if I'm talking about the future, I don't really care that it started at 10. So I'm really just looking at the fact that the tank has 200 in it. And then I'm saying this is kind of what's pouring in, which means that's the concentration. Wait a second, 7 kilograms per liter. That's what's getting poured in here, 0.7. So what is 0.7? I'm just thinking out loud because I actually don't know the answer to this. No, that didn't work because 0.7 kilograms per liter times 200 liters is 140 kilograms. So it seems like that's the water that would be in here is 140. But then this is pouring into it too. So it feels like I got to think about that more. I can't can't see how I could get 84 simply. Like, do I have to do all this math, or is there something simple I could? But I'm not seeing it. If there is one. Anyway, okay. Let's leave it at that, so that you can ask me test questions or whatever. But obviously your brain's probably full too. So as usual, I'll post that, and I'll show you the cool shortcut tomorrow.